Hi there, my name is Mike and welcome to my channel. In today's video, we're going to cover something called homogeneous functions. Specifically, we're going to talk about it because a lot of people learn this in their first course of differential equations. They'll ask you to quantify what is a homogeneous equation. Unfortunately, they won't really tell you what a homogeneous function actually is. They just say, here's what to look for, that's how you know to solve it, go from there. And it's annoying because you never learn what this actually is, and you lose a lot of the intuition because of it. So today, I want to talk about what they are. I'm going to give you the intuition to understand what a homogeneous function does, why it's important, why we're learning this. Then we're going to show you how to test it every single time. So you won't just need to learn, okay, does it have the right terms in the right locations? Is there pure functions of x? We're going to avoid that. I'm going to show you a test that'll work every single time. Then we'll go over an example, and finally, once you've got some familiarity with this, you'll see how you can quickly tell and why the lecture notes that probably told you to do it the quick way weren't so bad. So without further ado, let's get right into it. The first thing we're going to talk about is that what is a homogeneous function? And I'd like to start with give you an idea of what homogeneity means in a material science sense. So let's take a homogeneous material. And a good example for this might be a piece of paper, just like the one we were writing on. If I take this piece of paper, every single bit of it has the same paper structure, maybe except for the part that's sticky. But for now, let's ignore that. So ignoring the sticky part of this sticky note, every single piece, if you could look into a microscope and see the molecules of paper, are more or less the same. And most importantly, the paper is the same here as it is over here. They both look the same, they both have the same molecules in them, they have the same pigment. For all intents and purposes, I could cut these circles out, and assuming they were the same size and shape, I could flip them, and there'd be no difference that you could tell. That's what homogeneity is in a material sense. It means something that is completely uniform. Think of a squad of soldiers with the exact same uniform. They are homogeneous among themselves. So homogeneity is actually a really useful property. And the reason it's useful is because we study differential equations to learn about how the rate of change, let's say dy dx, is influenced by some function f of x and y. So it's useful then if we were to know, let's say someone whispered in our ear and told us that, hey, if we increase the function that we have, f of x and y, by a certain amount, some scalar quantity, call it the Greek letter lambda, just any variable, okay? If we increase this function, what if they whispered in our ear and told us, hey, did you know the slope is also going to increase at somewhere around the same? Maybe it's lambda squared, but maybe it increases together. That might give us some clues as to find out additional information about this function and allow us to solve a tricky ODE. That's why we study homogeneity. Unfortunately, they don't really build the intuition for you. So I'm going to show you the mathematical definition for a homogeneous function. Maybe you'll see how that relationship where the function is the same one place as it is another, maybe you'll see how from the mathematical definition we get to that logical conclusion. So let's go ahead and look at it. The test for homogeneity is as follows. If I have a function f of, and this is the general sense, okay? This is for any function, not just differential equations, but we'll show you the differential equations case in just a moment. So let's say I have any function f of x comma y, and right now we're just saying, yep, it's equal to f of x and y. The function is itself. This is correct. What we want to do, the way we test for homogeneity, the way we mathematically define it, is we say, let's take that x and y point, all right? And let's say I have a point called x naught, y naught. If I multiplied them evenly, so that means x gets the same multiply, y gets the same multiply. If I multiply them evenly by a scalar, lambda, the Greek letter, again, you can use any variable, then the output should be very specific and measured. And it ends up being very specific and measured indeed. So we say f of lambda x, f of lambda y, is going to spit out f of x and y, but it's going to be multiplied by some constant lambda raised to the nth power. And this is actually very interesting because here's what's happening here. We multiplied x and y by some constant, and the function actually stays the same. The information for like the core function, the bare bones structure, is still there. We just have a little multiplier, and that multiplier is proportional to the one we put in. So let's go ahead and use an example. We're going to use the function y prime, this is going to be a differential equation example. That's very important for us. So we're going to use the function y prime minus 3x equals 6y. Now the first thing we want to do whenever we look at equations like this is we want to bring them to a standard form. And the standard form for dealing with proving homogeneous functions, the standard form you should aim for any differential equation is you want to move everything so you get something on the order of dy by dx is equal to some function f of x and y. So to do that, here is our dy by dx, right? Y prime dy dx. It's the same thing. I'm just using different notation to get you familiar with it because your professor might try something like that. So get an idea of it. And then we need to have it equals to f of x and y. So here's a function of y, right? This is f of y. This looks like a function of x. So what's it doing all the way over there? Let's move it over here. So now we can rewrite this as y prime, which is the same as dy by dx is equal to 3x plus 6y. And this is our new function to work with. Now the way we're going to test for homogeneity is super duper simple. We are going to take x and y, all right? And we are going to say that we are going to multiply them, scale them by some constant lambda x and lambda y. Now here's what's going to happen. We're going to plug this in. It's as simple as it looks. We're going to plug this in and substitute in just like this. And when we do that, we get 3 lambda x plus 6 lambda y. Now if we ignore these parenthesis signs, you notice that each term has a lambda cofactor. We can pull that out and factor a lambda and get lambda times 3x plus 6y. And that is the original f of x, y. So we've managed to do the exact thing that we were hoping for. We've proven homogeneity. And we'll go ahead and give you one more example that shows you a little bit more what happens if something else, maybe it doesn't look as clean as that. I gave you a very easy function there. So let's use a different one. Let's say our function is y prime of 7x minus y is equal to 2x plus 3y. Okay, immediately the first thing you should notice here is that these two obviously are not, this is not a linear function because that y prime is going to be multiplied by that y. We're not concerned with linearity right now. In fact, if you don't even know what that means, that's fine. I just want you to know that if you see something like this, your brain might start to ring some alarm bells going, oh, that's not what it's supposed to look like, because you're thinking about linearity. And remember that a function being homogeneous is different than a function being linear. And you can have a nonlinear function that's homogeneous, you can have a linear function that is non-homogeneous, and it's important to keep that distinction in mind. So again, we want y prime on its own. So let's go ahead and divide this term over to the other side, and we're going to have dy by dx, it's the same as y prime, is equal to 2x plus 3y over 7x minus y. So here's our function. Let's go ahead and do the same lambda substitution. So this is going to turn into 2 lambda x plus 3 lambda y over 7 lambda x minus lambda y. Let's pull that lambda out on both sides, and if you're paying attention here, you should be able to see what we're going to do here. This is going to end up being lambda over lambda times 2x plus 3y, 7x minus y. And what do you know? The lambdas cancel. So is our initial test still true? Did f of x and y give us lambda times f of x and y? It sure did, because what we're looking at is lambda to the 0th power, which is just 1. So everything works. And this works the other way too. You might even find that sometimes when you do this test, you end up with a lambda squared. Totally normal. You might even end up with a lambda to the 4th or 5th or 6th power. That's normal. So the nice thing about this test is it gives you a defined way to work with these things. So that brings us to our last point, and that is how to quickly tell if a function is homogeneous or non-homogeneous. And the quick way to do so, and there's a formal definition that we can use, and I want you to look at every single term of the two equations we've practiced on, and notice that they have something in common. First of all, let's classify these terms. We want to be very precise in mathematics, so we're going to call this a non-zero term. Right? I mean, we're just stating the obvious. But when we're doing math, it's important to be explicit like that. We can say that every single non-zero term has an x and a y like this. So what this tells us is that every single non-zero term should not be a constant. We should not see something like plus 9. Because if we do, we won't output a function that is perfectly homogeneous. And it could be a small difference. You know, if I had the function we just had and we had plus 0.0001, we'd still not have a perfectly homogeneous function. Because when we added that lambda in, we couldn't algebraically pull out the lambda as perfectly as we did. There'd be this new 0.0001 that did not get affected by the lambda. It's like taking our piece of paper that's homogeneous from earlier and poking it right here. And now there's a little hill in the paper, but everything else down here is the same, and it's no longer a homogeneous material. Where when we multiply by lambda, we take that whole paper and we just do something that's equal to it. If I move a little bit of the function, the paper this way, it's no longer homogeneous in space. If it starts planar like this, and I homogeneously modify it, it's a homogeneous piece of paper, I scale it by some even factor lambda, and the whole paper is going to come up, just like that, evenly. So that's what we want to look for. It's even change. If I pump up some big scalar factor into x and y, we should see an equal big pump up in whatever that function outputs. So much so that we can pull out algebraically the factor that we pulled out. And that's the idea with a homogeneous function. Hopefully you have a better insight of why this is important now. If you still have any questions, let me know in the comments below, please, as well as recommendations for anything else you'd like to be clarified on or learned. And lastly, if you did enjoy this content and you found it useful to you, a like and a subscribe goes a long way. Thank you so much. I'll see you guys in the next one. Peace.